Yeah, so it's a great pleasure to have this opportunity to talk here. It actually gives me the rare opportunity to be in Tel Aviv in August. Quite an interesting experience. I never knew it's so active here during the summer. What I want to discuss is some two general techniques that have been quite successful in discrete mathematics in the last decades. And I'm pretty sure it will keep being successful in the future too. And I'll try to give you some examples that illustrate these techniques and then maybe make some speculations about the future. Now, I was told that this videograph is not focused. Maybe try to. So there are a lot of algebraic techniques that have been used in discrete mathematics and that I'm not going to discuss. So this includes the use of representation theory for enumeration problems, includes the application of spectral techniques in the study of highly regular structures and in the study of pseudo-random graphs. Well, we heard something about this in the previous lecture of Lovas. Rather, what I want to do is to describe two very simple examples where we use algebraic methods to get something in combinatorics. One is a technique that I like to call combinatorial Nullstellensatz, and another one is the dimension or a rank argument. So let me proceed to tell you about this. So here is just reminding you Hilbert's Nullstellensatz. So what it says is that if we have a polynomial in the ring of polynomials over an algebraically closed field, and if it vanishes over all the common zeros of an ideal, then some power of the polynomial lies in the ideal, right? So this is something that we all know. And I want to consider a very simple special case of this, actually. But in this special case, we can say a bit more. And here is what it is. So this special case is the case where the number of polynomials generating the ideals that I'm considering is equal to the number of variables. And each of the polynomials that generates ideal is a polynomial with one variable. So it's of the form gi that you see there. And in fact, even all its roots are in the field. So it's really a very simple case. And then the claim is, and it's not too difficult to prove, but I'll try to convince you that it's useful, that the claim is that in this case, if we have another polynomial f that vanishes over all the common zeros, so whenever the gi's are zeros and so is f, then we know by Nullstellensatz that some power of f lies in the ideal, but actually now f itself lies in the ideal. And moreover, if we write f as a linear combination with polynomial coefficients of the generators of the ideal, then we can say something about the degrees of these coefficients. So in some sense, there are no cancellations here, or the degree is as low as you could hope that it would be. And just by looking, somehow equating coefficients of the highest terms in both sides of these, then we can get the following, which is, again, you can think about it just as extending the fact that a polynomial of degree k cannot have more than k distinct roots unless it's identically zero. So it says the following, that again, I have a field, and I have a polynomial in the ring of polynomials over the field. Its degree is the sum of ti's. Ti's are just some integers, no negative integers. And we have some non-zero coefficient. So the coefficient I want to assume that is non-zero is a product of the xi to the ti's. This is not zero. Then if you give me sets in the field, and Si is a set of cardinality bigger than Ti, then I can find an element, little si in capital Si, so that if I plug these elements in the polynomials, then I get something which is non-zero, right? And I want to show you some applications of this. So someone once told me that the difference between a trick and a general technique is that a general technique is that it's really a trick also, but you can apply it in at least two seemingly unrelated situations. So I'll try to show you some seemingly unrelated situations. And the first one, so I'll use this. The first one is a classical result of Cauchy and Davenport, a simple result, I should say, in additive number theory. And it says the following, that if P is a prime, right, and in ZP, in the finite field, here we really use only the additive structure, so in the abelian group Z mod P, we have two sets, two non-empty sets, A and B. Then if we look at the set of all sums, all the sums of the form little a plus little b, where little a is in capital A and little b is in capital B, and we look at the cardinality of these, then, well, either we get everything, but if we don't get everything, then the cardinality of what we get is at least the cardinality of A plus the cardinality of B minus 1. And that's tight. Whenever we take two arithmetic progressions, modulo P with the same difference, then this is what we really get. So this was proved by Davenport in 1935. He was interested in proving a discrete analog to a question of Khinchin at that time, about that had to do with the Shnirelman density of a sum of two sequences. Now this conjecture of Khinchin was subsequently proved by Mann several years later. But meanwhile, the result of Davenport was extended by Chola and Shepardson, was considered.
Khinchin proved a special case.
So actually, I mean, this one, Landau indeed wrote about this also, but Khinchin, his conjecture was about the Shnirelman density of the sum of two sequences, right?
No, it was Landau conjecture, I guess, no?
So not as far as I know. I mean, Landau definitely was involved, so he wrote about this, but but as far as I know, Mans, or definitely Mans in his paper, he talks about the conjecture of Khinchin, but it's okay. So, I mean, could be that Mann didn't, but okay. So this is. Let me, by the way, encourage you to make remarks and comments, and preferably hostile ones, actually, if you will, because that makes it more lively. So, all right, but so it could be. So anyway, this is so this was, as I said, was considered indeed, and as was said here, was considered also by Landau, and really became one of the fundamental results in additive number theory. Now, sometime later, so in 1947, Davenport published another note where he mentions that he found out that exactly the same thing was proved by Cauchy, naturally sometime earlier, so that was in 1813. Well, Cauchy, in fact, was interested in giving an alternative proof of a lemma of Lagrange in his paper, proving that every integer is a sum of 4 squares. But now both proofs, so if you look at them, the proof of Cauchy and the proof of Davenport are very similar. They are elementary, combinatorial, they are by induction, and they are pretty simple, so you can try to think about it. I mean, it's one of the things that is simple after you know it, but so it's not necessarily so simple to find, but it's really a few lines. Now I want to show you another proof of that, which is just as short, and it uses this thing that I said here. We just substitute in it. So this we found a few years ago with Nathanson and Ruja. I mean, as I said, these proofs of Cauchy and Davenport are very simple, so it's not clear why we want an another proof, but still I want to say something about it. So we just take these things that we see here, and we plug it in the right polynomial. So let's assume that we have a counterexample to this Cauchy-Davenport theorem. So we have two non-empty sets A and B. I mean, I'm now in the non-trivial case where we don't get everything. And their sum is too small, so the sum is contained in some set C, which is too small, is of this cardinality. Then we can look at this polynomial, the product of x plus y minus c over all small c in capital C. And then it's easy to see that if I define T1 to be the cardinality of A minus 1 and T2 to be the cardinality of B minus 1, then the corresponding coefficient of x to the T1 times y to the T2 is non-zero. It's some binomial coefficient, which is non-zero modulo P. And because of this, for the two sets A and B, as S1 and S2, we can find an element in A and an element in B, so that if we plug it in this polynomial, we get a non-zero. But that's impossible, right? Because we have here the product over all the c's in little c. So in particular, one of the terms here is going to be 0, and therefore we get a contradiction. So as I said, this is just another proof, and but the interesting thing about it is that it gives much more. So it definitely gives a lot of things that we do not know how to prove using the combinatorial approach. And I just mentioned one of them. So here is something that if, again, P is a prime, and you take in the group of the integers modulo P, K non-empty subsets now, let's say of pairwise distinct cardinalities, and you look at the set of all sums, so I denote it here by some circled sum, of all the sums of the form little a1 plus little a2 plus and so on plus little ak, where little ai is in capital AI, and the ai's are pairwise distinct. I don't want to add a number to the same number twice. And I ask how many of them I can get. And then it turns out that the answer, and again, it's a tight answer, so you can give examples. It's always tight for all possible cardinalities of the AIs. Either you get everything, or if not, then you get at least the sum of the cardinalities of the AIs minus some binomial coefficient, k plus 1, choose 2, plus 1. And the proof is kind of identical to the one I told you, only you write some slightly more complicated polynomial, which here would be a product of a van der Monde polynomial with a van der Monde determinant, with some polynomial which is the sum of all the xi's minus something. And here again, to apply this simple things that I told you here, you have to prove that some coefficient is non-zero. In this case, it's somewhat more complicated, so it's not a binomial coefficient, but it's a more complicated quantity. But the lucky thing is that this quantity appears. It appears in the Ballot problem, so it really counts monotone lattice passes, which are passes that go from the origin to some place, keeping the relative order between the coordinates. And this is also known to be the number of Young tableau of a certain shape, which is also the dimension of the corresponding irreducible representation of the symmetric group. So we really have the Hooke formula for that. We can just plug in it. We get something that fortunately is non-zero modulo the prime. And therefore, we again plug in the same thing, and we get the consequence that we want. And one can keep extending this, so you can use some other identities like the Dyson conjecture, or because the trouble is that you always have to prove that some coefficient is non-zero, and you can get some results of this type. Maybe I should say that even a very special case of this, so if you take here k equals 2, and even a special case of k equals 2, where the two sets are kind of the same, one is obtained from the other by forgetting one element. So that was a conjecture of Erdős and Heilbronn, on which there were many partial results, and actually it was proved by Dias de Silva and Hamidoun, and that also gives it. Now let me mention a more combinatorial application. Maybe it's time to this is a more combinatorial application of the same general thing, and that has to do with graph coloring. So what I'll describe comes from a paper with Miki Tarsi. And there are some related, although not quite the same, but somewhat related much earlier results of Matyasevich. And actually, very recently, he wrote me about some recent ideas that he has about this, which, okay, maybe I'll mention them later. So here is, again, I'll say very little about this, but I want to talk about graph coloring, so let me put the definition. When we have a graph, G, V is a set of vertices, E is a set of edges, then we call a coloring of the set of vertices, it's just a function from the vertices to the integers, let's say colors with the integers. So it's an assignment of a color or an integer to every vertex so that adjacent vertices get distinct colors. For example, here you see a coloring of a cycle of length 5, proper coloring by 3 colors. Adjacent vertices here have distinct colors. And the chromatic number of the graph is a minimum number of colors required in a proper coloring of it. Right? So this is just a definition. And now we want to use some polynomials here. And there is a so-called graph polynomial introduced by Sylvester and Peterson. Actually, Sylvester did it first. But Peterson was the one who really used it in invariant theory. That's in the previous century. And it's a very simple polynomial. So when you give me a graph, let a set of vertices be denoted by 1 up to n. Then we associate every vertex with a variable. And the graph polynomial is the product over all the edges of xi minus xj. Right? So this is just now here is a very simple remark that just from the definition it follows that if you give me some list of colors, so let's say that I'm supposed to color the first vertex by something from S1 and the second by something from S2 and so on, and the nth vertex by something from Sn, then there exists a proper coloring using assigning vertex number I a color from Si, if and only if there exists some little si and capital Si, so that when I substitute them in the graph polynomial, then I get non-zero. Right? So it's just from the definition. And this, of course, looks as the consequence of the theorem that I had on the slide there. So hopefully, one would be able to do something if we can interpret the relevant coefficients that we have to show that it's non-zero, if we can interpret it combinatorially and prove in some way that it's non-zero. Now, so whenever you have something that looks new about coloring, the first thing to try is the four-color theorem, right? So the four-color theorem is by far the best-known result in graph theory, probably in combinatorics. It's a statement that every planar graph is four-colorable. This was conjectured by Francis Guthrie in 1852, was proved by Appel and Haken in 76. There is another related proof by Robertson, Seymour, Sanders, and Thomas. And both proofs make heavy use of computers, as you all know. So they make heavy use in the sense that also to check the proof, we cannot do it without using computers. And of course, it would be very nice to find a more conventional proof. And a lot of people tried to do this thing. So of course, I don't know to do this thing, but here is something that one could get from these ideas, and it's kind of interesting, I think, and it's an extension, so it's a stronger theorem than the four-color theorem. The proof uses the four-color theorem, but it uses it in a strange way, so I'll tell you how it comes. And it goes as follows. So there is an old result, simple result, by Tate from the previous century that says that the four-color theorem is equivalent to the following statement, that if you have a planar, cubic, two-connected graph, so let me say what this is. So we have a planar, you see a picture here. You have a planar graph, so it can be drawn in the plane with edges being straight lines and no intersections, let's say. And it's two connected, namely, we cannot separate it by deleting one vertex or one edge. So whenever we delete an edge, it stays connected. And cubic means that the degree of every vertex is 3. So in every vertex, we see 3 edges. Then what Tate proved is that the four-color theorem is equivalent to the statement that the edges of each such graph can be properly colored by 3 colors. So we are allowed to use the colors 1, 2, 3 to color the edges, and adjacent edges should get distinct colors. Right? And that's equivalent to the four-color theorem. Now here is something which is somewhat stronger, and for this one has to use some of these things. But so suppose you give me such a graph as you see in the picture here: planar, cubic, 2 connected. And now for each edge, you give a list of 3 colors. So now not all the edges are allowed to be colored by either 1 or 2 or 3, but they can use any of some 3 colors. So you see that this edge I allow you to color it by blue, red, or green, and this edge you can color it by, I don't know, white, red, or green, and so on.
Oh, that's 3 colors.
3 colors, because, right, yeah, because once we move to the edges, then the four-color theorem becomes like a 3-color theorem, right? And that's equivalent. It's,
here in the picture you have 4 different colors.
Well, in the picture, maybe I thought I have 5 here. Maybe I have 5, but because I have black also. But it can be arbitrary many. So altogether, we have here as many colors as you want, n colors. I don't know. So no restriction on the number of colors. Then still, the claim is that you can find there is a proper coloring, assigning to each edge a color from its list. Now, that would look pretty obvious that somehow the situation becomes only easier if we have distinct lists to distinct edges. But actually, this is not the case. So one can show examples with coloring of vertices where the situation becomes more difficult if we allow lists. But still, you could hope that maybe, I mean, the way to reduce it to the four-color theorem is still by somehow showing that the most difficult case is when we have the same list. But it's not. I mean, the only way that we know to prove it is that somehow you write down this polynomial. This polynomial is the product of a lot of Vandermonde determinants and some things. You look at it, you have to prove that this coefficient is non-zero. This coefficient, because of some old results of Vineron and Gégère and others, you can show that actually, miraculously, or, well, this word was used in the lecture before, so I should be careful with it. But somewhat surprisingly, this, but there are no comments about it now. So somewhat surprisingly, this coefficient actually counts the number of usual proper colorings of the edges of the planar graph, which by the four-color theorem is non-zero. So I don't know if, I mean, yeah, I think I'm now probably, I have less hopes about really getting the four colors theorem from this algebraic approach, but Matiasevich is telling me that he still has high hopes, and he has some different way, but also using some polynomials to get something. So maybe, all right, but let me leave this combinatorial Nullstellensatz, and let me talk about what I want to call the dimension rank argument, and it's an opportunity to, and again, I'll give just one. So that's a much more widely used technique, which has been used a lot, and again, I'll try to illustrate it by one example, talking about so-called Shannon capacity of graphs. We don't, yeah. And let me tell you something about graph powers. So I'm starting something new. If you lost me, this is the time to start listening again. Don't have to, but you can. So here is a definition of a product of two graphs. If we have a graph G, V is always a set of vertices, E is a set of edges, and H is another graph, then their product is a graph whose set of vertices is the Cartesian product of the set of vertices of G with that of H. And two vertices, UV, is adjacent to U prime, V prime, even only if in every coordinate, well, in each of the two coordinates, they are either equal or adjacent, but they are not equal in both. I don't want loops here. Okay, so this is, this product is associative, and we can define the nth power of a graph is just by taking G and multiplying it by itself n times. So now the vertices are vectors of vertices of length n of vertices of the original graph, and two are adjacent, even only if in every coordinate they are either equal or adjacent. And we'll see that there is some motivation to define the product in this way. But now here is a definition of the Shannon capacity of a graph. So it was introduced in a paper by Shannon. He didn't give it this name. The name was given by Lovas in '79. And here is how it goes. So we take a fixed graph G, we take the nth power of it, and we take the independence number of that. So that's the maximum number of vertices in the nth power, no two of which are connected. And then we take the nth root of that, and we take the limit as n goes to infinity. So it is easy to see that the limit exists, because for every fixed G, this function alpha of G to the n is super multiplicative. So the limit exists by Feketev's lemma, or anything you want, and it's equal to the supremum, right? And we want to know something about this limit. Now maybe I'll first say something about the motivation. So obviously it comes from information theory. Usually I found out that it's good to put the picture of Shannon in the definition. So here is a motivation. So what you see here is a definition of a channel. What is a channel? A channel has inputs. There is a finite set, which are all the sets that, of possible inputs the channel may want to send to the other side. There is a possibly infinite, but here we can think that's finite also, set of outputs, y. And then there is a fan-out set for every possible input, little x in capital X. There is a fan-out set S sub x. And the way to think about it is that when Shannon is sending to the other side little x, then what arrives as an output is something from the fan-out set. Now, usually in the definition of a channel, we have also a probability distribution that tells us with what probability we take everything from the fan-out set. But here we will be interested in the zero error capacity, and therefore I just put in the fan-out set everything that can appear with positive probability. Now, when we have a channel, we can define the graph of the channel, and the graph of the channel is a graph whose set of vertices are just all the possible inputs, and two are adjacent if they are confusable, if the fan-out sets of them intersect. Namely, x and x prime are adjacent if when Shannon is sending x or when he's sending x prime, on the other side, what we could get is the same thing. So it's confusable. And the definition of this and the definition of a graph product immediately says that the independence number of the graph of a channel is just the maximum number of messages that we can send in one use of the channel with no danger of confusion. So we will somehow look at the graph of the channel and decide that we are going to use only symbols from this independent set. These are symbols that are never confusable. Right, so maybe in English, P and B, I'm afraid that they look about the same, so I'm going to use only P. And this we decide in advance. And okay, so this is the independence number. Now, one of the main things of in information theory is that when we use longer communication, then things become more efficient. And therefore, if we want to send here longer messages, then again, from the definition, it follows that the independence number of G to the n is the maximum number of messages of length n that we can possibly send with no danger of confusion. Because you see, two things are confusable, even only if in every coordinate they are confusable. Right? If even in the seventh coordinates are not confusable, the seventh coordinate will tell me which one had been sent. Right? And therefore, the right way to think about this Shannon capacity is that it's the maximum number of distinct messages per one use of the channel that can be sent when we are sending very long messages. right? So in other words, this is the effective alphabet size. If the capacity of a channel is 7, then a good way to think about it is that if I'm sending very long messages, then I could think that actually I have an alphabet of size 7, but now I don't have any errors at all. So whenever I send something, then I can reconstruct it. Okay. Now it's pretty amazing. I mean, this definition of the Shannon capacity, maybe it's not so obvious, but it looks something that we can deal with, maybe. So it's a limit of some simple quantity. And it's amazing how difficult it is to compute it. So just to give you an idea about this is that despite some reasonable amount of efforts, this capacity is not known, suppose I want to know it precisely, for really simple graphs. So for a cycle of length 7, for example. If we take a cycle of length 7, then it's not known what is the Shannon capacity of it. That's pretty amazing. I mean, we can approximate it, and there are pretty good approximations, but now in general, there are some, so lower bounds for Shannon capacity, usually we get them just by constructing some independent sets in the graph, in the second power of it, the 7th power of it. We said that this limit is a supremum, so every independent set in some fixed power of the graph would give me a lower bound for the Shannon capacity. For upper bounds, there are several bounds that are known. So the first one is due to Shannon. It's combinatorial or polyhedral, if you want. Then the best known bound is a bound of Lovász. It's called the theta function. That's a geometric bound. And it has several interesting properties. It is efficiently computable, which is important. It satisfies some dual relation, which is also important. Then there are some other bounds of Hemmers. And I want to tell you some yet another bound, and that would be my example of kind of using this dimension argument. So here is another bound. You call a representation of a graph over so you take some linear space of polynomials over a field. It doesn't have to be all polynomials, so it can be all polynomials of degree at most something called multilinear polynomials over a field of characteristic 5, whatever you choose. You take this linear space of polynomial, and then we call it script f, and you say that the graph G has a representation over this script f if you can associate each vertex v with a polynomial in this linear space of polynomials, polynomial f sub v, and an R tuple. Let's say that the polynomials are in R variables, so I think I said R variables, right, so and an R tuple of elements of the field, and it has to satisfy some two simple relations. And the relations are that if you substitute CV in f of v, in fv, so the same, the R tuple assigned to a vertex in the polynomial assigned to the same vertex, you get non-zero. And if you substitute the R tuple assigned to another vertex in the polynomial assigned to one vertex, and these two vertices happen to be non-adjacent, then what you get is 0. If they are adjacent, then you don't care.
F sub v is your polynomial assigned to the vertices.
To vertex number v, to the vertex v.
C sub v again.
And C sub v is the R tuple assigned to vertex v. It's an R tuple. So for each vertex, we assigned a polynomial and an R tuple of something that we can substitute in the polynomial.
So you assign two things, polynomial.
That's right, polynomial and number, right. And a sort of R tuple of numbers, right. And
what is R?
R is just the number of variables in the polynomials, right? Because we are, right. So it's, okay. And then what one can prove, and somehow a simple application of this dimension argument, is that if the graph G has a representation in this sense over f, over this linear space f, then the Shannon capacity of the graph is at most a dimension of this space. And the way the proof goes is essentially that we have to bound somehow the cardinality of an independent set in some high power of the graph. So we take an independent set in some high power of the graph, and we use the representation to assign to each element in this independent set a polynomial. Well, not a polynomial in the original set f, but in the tensor power or product of it with itself many times. And then we show that the way we assign these polynomials to the vertices in the big independent set in the power is such that the polynomials assigned to distinct members of the independent set are linearly independent. And then because we have some bound on the dimension of the tensor power of things that we started with, then what we want follows. Now, maybe I just mention some application of this. So here is and it's the following that I want to argue that is somewhat surprising or counterintuitive. That what it gives is that we can find two graphs, G and H, some construction of some graphs G and H, or family of graphs G, of pairs GH, so that the Shannon capacity of G is small and the Shannon capacity of H is small, but if we take their disjoint union, then the Shannon capacity of the union is very big, is much bigger than the sum. So Shannon proved actually that the capacity of the union is always at least as big as the sum of the capacities, and equality holds in many cases. And he asked if equality holds always, so this says that it's not. And I mean, I want to say that this is somewhat surprising. So intuitively, what this says is the following, that you have two very small channels, you know, like you have this English alphabet, that you have 26 letters, and maybe some of them are confusable, but let's say that the effective alphabet size is still 26. We can send, then you have the Hebrew alphabet, which has 22 letters, trust me on that. And then we can suppose that we have now both channels, and we can use in each, whenever we send a symbol, we can send either a Hebrew letter or an English letter, and they don't mix. And we can decide what we are choosing. So these examples really say that there are examples of English and Hebrew, so to speak, so that if I have these 22 letters and these 26 letters, effectively, then effectively, if I can combine them, then maybe I'll have 1,000, right? So it's kind of...
So these are carefully concocted examples.
That's right.
So what's the typical, the typical set?
Right, yes. So, right, so for example, a typical graph is a random graph, let's say, or so for a random graph, I don't know. I mean, I suspect that something like this holds for a random graph and for its complement. It should be true, but I don't know to prove anything. That's right, that it jumps. If the pair are a random graph and its complement. So there should be some connection between the pair.
Random graph which is small, either random graph with complement, or the both here are the small.
Right, so that would be a conjecture, let's say. So I think it's not known, and the only thing that is known is that a random graph, that the capacity of a random graph on n vertices is not more than something like square root n. But it should be true that the capacity of a random graph is about log n, I think. And if this is true, but that's not known. If this is true, then there would be such a jump from now I should say that that here it was very crucial that in the previous bound that I told you, you are free to choose the field in which you are working. So it's very important that when you bound the capacity of this graph G and the other graph H, that you use different fields. Because actually, if you would use the same field twice, or if you use some of the existing, say the theta bound of Lovász, then you will not be able to get such an example, at least not in such a way. Anyway, so let me, I'm in a pretty bad shape in time, not only in time.
Maybe you should continue simultaneously in Hebrew and English.
Right, yeah. But in fact, definitely, if I could have talked in your pace, even in English, then I would have been done by now. But it's so let me still try to say something about probabilistic methods, not too much. And actually, let me even use this break between the two to remind you that there is a reception today in 7:30. So that's a good time to, so even, right. So even if you didn't understand anything from what I said until now, then there is a reception in 7:30, and it's, okay. So As a mathematical theory, probability is usually said to have begun with a later correspondence between Pascal and Fermat in the 17th century. They were interested in splitting the bets in an uneven cube game. But the rigorous mathematical foundation had to wait really to the creation of measure theory. This was with the thesis of Lebesgue in the beginning of this century. And that enabled Kolmogorov to define in the 30s the basic notions of probability, like a probability space, a random variable, expectation as an integration, and so on. Now, it would probably be fair to say that, that probability now is some part of analysis, but we'll be interested in the next 5 minutes in applications of probability in discrete mathematics. So let me say something about what is called the probabilistic method. So this was realized by several researchers at least 50 years ago, and probably there were examples in analysis, in number theory, but maybe even more strikingly in combinatorics, where we deal with very basic structures and still probability somehow helps. And there's a main name to mention is Paul Erdős, who is really the creator of what we call now the probabilistic method, which in one sentence is the following naive sentence that you see here, that to prove the existence of a structure or a substructure of a given one with some desired properties, what we do is that we generate some probability space with some candidate structures, and we show that a randomly chosen point in this space satisfies all properties with some positive probability, and therefore it exists. And I'll just show you what was historically the first, or one of the first, but maybe the first important application, and that was lower bound for Ramsey numbers. So let me say something about the Ramsey number. So Ramsey theory in general says, maybe philosophically, that complete disorder is impossible, and in the special case of graphs, it says that there exists this number R of k and t for every 2 integers k and t. The number R of kt is finite. The smallest number, so that every graph with R, k, t vertices or more, either it contains a clique of k vertices every 2 of which are connected, or it contains an independent set of t vertices, no 2 of which are connected. And as I said, the fact that all these numbers are finite is a result of the mathematician and economist Frank Plumpton Ramsey in 1930. So he proved that all of them are finite. He also proved a much more general statement, and essentially the same proof for hypergraphs and for the infinite case. As was mentioned, actually the infinite case in a way is easier. And then this was reproved by Erdős and Zakharov, who also got a bound for it. So we have some bound for this in terms of some binomial coefficient. Now, actually, I mean, there was some discussion last week and also this week about good and bad problems, and I usually like to think that it's a matter of taste, but I agree that we all have to decide for ourselves at least what are good and what are bad problems. The Ramsey, right? So you want to? So here is a bad problem. So I think this, so a bad problem would be to try and find exactly the value of the Ramsey number R46, for example. Now, despite the fact that it's a bad, or I think it's a bad problem, there was a lot of effort done on really finding exact Ramsey numbers, and this is because it is indeed a natural problem. So for discrete mathematicians, if we know that a number is finite, then the most natural thing is to try to find it. And indeed, people tried to find, so here you see actually, I mean, these numbers, I mean, this Ramsey number is symmetric, and the blue numbers are trivial from the definition. The red numbers are all the numbers that are known precisely. So these are all the Ramsey numbers that are known precisely. There are bounds for the others, and the more complicated ones were found by a lot of computer search and some clever ideas, of course, as well. But now, on the other hand, what I think is a better problem is to know the asymptotics of these numbers. And then there are some bounds, and And as I said, the first kind of interesting application of the probabilistic method was by Erdős in 47. That's a lower bound for the Ramsey numbers. And what he proved is that this R of kk, which by the bound I told you that is already there, is at most 4 to the k, roughly. He proved that it's at least square root 2 to the k. And the paper was 3 pages. And today, the proof would be like one line. We would say, take the random graph and do the obvious computation. And still, it was kind of a big surprise. And in a way, it still is, because we don't know, we don't have any idea of how to construct such graphs explicitly. So it still gives and the same argument, although this was done later, but basically the same argument in Erdős's paper gives it for fixed value of t, then for fixed value of k, then for I, k, and t, you get such a bound, where c depends on k. So that's an example of a probabilistic statement. I wanted to give, there are some more striking examples where you actually prove a deterministic theorem where really nothing in the statement suggests to use probability, but let me not talk about this, because I want to use my last, how much?
7 minutes.
My last 7 minutes, so 6, all right. For the, not more than 7, definitely. I noticed that yesterday everybody promised, when they asked how much time they have, they promised that they would use less, but nobody kept his promise. But I'll try to. So I want to say something in the last 5 minutes, about the algorithmic aspects of these techniques and others. So again, it would probably be fair to say that that one of the main reasons for the development of discrete mathematics in the last 2 decades was the tight connection to theoretical computer science. And this connection to theoretical computer science suggests the study of the algorithmic aspects of algebraic and probabilistic proofs and other proofs in combinatorics. And here are 2 questions that one can ask. So one of them is, can algorithmic problems corresponding to existence, algebraic or probabilistic or topological or other proofs, can they actually be solved efficiently, right? So I'll give some example. And then another reasonable question is, can a combinatorial structure whose existence is proved by a probabilistic argument, like in this construction of Erdős, can we construct them explicitly? And explicitly, there is some explicit definition of it, and I should say also that constructing them explicitly or efficiently would also have applications, again, algorithmic applications, because these pseudo-random structures can be used in some de-randomization or some. So let me, here is an example. So I told you that every planar, cubic, 2-connected graph, together with a list of 3 colors for every edge, you can find the proper coloring using the list. Now, can we actually do it? I don't know how to do it efficiently. I mean, the fact that this coloring exists is because some coefficient of some polynomial is non-zero. Suppose I give you now, here is a graph, and here are the list of colors. Now find, we know that there is this way to color them properly using the list. Can you actually find one? Well, we don't know how to do it. Here is a much more general thing, which probably is hopelessly difficult, but it would be very nice if some general result from algebraic geometry or something can be used to do it. So here is an algorithmic problem that I have a field and I have a polynomial in the ring of polynomials over the field, and it satisfies this property that I told you. This coefficient is non-zero, and I am given these sets that are big enough. I know because of this Nullstellensatz that there is some SI in capital SI such that the polynomial there is non-zero. Can we find such a thing efficiently?
I know it's the same oracle as before.
Well, but here I know there is a reason, right? So there is a reason because of, so it's not that an oracle told me, but I know the reason. The reason is, if you want, that a polynomial of low degree cannot have too many zeros, for example. So you'd hope that the proof, or maybe some other version of the proof, or
is not zero. The statement that this coefficient is non-zero, the question depends on the kinds of knowledge you have this coefficient.
Okay, so suppose I can compute the coefficient, right? In the example here, I can actually compute it, and I know what it is, and I...
So these effective now Stalingrad, Gromov, and people like that are...
Right, yeah. So I don't think that they give anything, right? So, right, yeah.
I think the best example is
but,
when you have an n by n matrix whose entries are linear functions in some variables, and you know this, it doesn't vanish, and you ask for a point.
That's right. Right. So again, but here actually it's different, because here I'll be happy also with a randomized algorithm, and in the matrix, in the determinant, we have a randomized algorithm. Here I would be happy to do it with randomization or deterministically or what have you, and still we don't. Now, explicit constructions. So of course, maybe the best example is to construct explicitly Ramsey-type graphs. There is one very nice construction, so that's really a remarkable paper by Frankel and Wilson, which does a lot of things, but one of the things it gives is an explicit construction for a graph showing that the Ramsey number RKK, well, it's not showing that it's exponential, but showing that it's more than polynomial, something like k to the log k over log k. Okay, and that's again an example actually of a dimension argument, somewhat more complicated than the one I described. Here is this construction gives nothing if we want a construction for RKT when t is fixed and k is big. I want to tell you something about some very recent thing about a construction, well, I guess k is fixed and t is big. So we want to get explicitly that this, again, somewhat grows. So it's at least t to the constant log k over log k. But I just tell you in one, because I think it's a good example to show what comes into it. And because often in these explicit constructions, you have to use a lot of sort of tools, advanced tools. And here is the construction I don't have here. So the construction is that you take this Q from the lecture of Don yesterday, and you have this finite field, GFQ to the R, right? I mean, anyway, there is no time to read anything here. And for every element x of the field, we let n of x denote the norm of the element over GFQ, which is defined here. It's not so crucial. And here is a graph. The set of vertices of the graph are sets of elements of size s. But not just sets, but sets so that the norm of every sum of two elements in the set is 1, right? And two are adjacent if there is a little a in a minus b and a little b in b minus a, such as the norm of this sum is also 1. Okay, and just, I'm not going to, but what is used in the proof is the following. So you have to use some spectral properties of some related graph. You have to use some character sums estimate, so basically Weil theorem or the Riemann hypothesis for curves. Then you have to use something, or that's the way now to do it, something from elementary algebraic geometry. So this was done actually by Kolar, Ronyai, and Sabo for some similar purpose. It's elementary, but it's not quite, so it goes beyond Bezout. It says something about and then you have to use some combinatorial result of Kovary, Shush, and Turan about bounds for the Zarankevich problem. And somehow, using all this together, it says that this graph has satisfies these properties. Last minute, let me just put, I have to mumble something about the future. So I didn't want to put some specific problems, although I mentioned a few during the talk. So there is no doubt in my mind that randomness and the related study of pseudo-randomness or explicit constructions will keep playing a crucial role in the development of discrete mathematics. This has something to do with de-randomization. We heard something about that last week, so let me not talk much about this. Now there is this issue of effective and non-effective proofs. So it seems obvious that we are going to have more and more non-effective proofs because we are going to see, and we already have a lot, of tools from other fields, from topology, from algebra, from probability, and all these tend to give us non-effective proofs. And yet, because of the connection to algorithms and to computer science, we really prefer to have effective proofs. So it will be interesting to see how indeed people will actually come to peace with this contradiction. So we will try to have more effective proofs, but on the other hand, it would be natural to use non-effective tools. And finally, there is this point that I didn't mention in this talk, but was briefly mentioned in the discussions last week, is that we will have to probably get used to the idea of the existence of computer-assisted proofs. And this is just because this tool is here, and there is I have no doubt that people will use it, not only in discrete mathematics, but in pure mathematics as well. So it doesn't necessarily mean that we all have to now rush and start programming, but probably means that we have to start thinking what is our attitude to these proofs, because if we can reduce the question to something that can be done in some finite amount of computations, then it's essentially solved, and probably we'll see more and more examples of this type. So let me finish this.